Hello.
Hey,
I had fun. It made me do the push phone verify thing.
right.
Ugh.
Hello.
Hello.
Hello, how are you?
Fine, and you?
Good.
So can you hear me well?
Yep.
Yes.
all good.
Yes.
Very good.
Hi, Professor Sohn.
Hi, Brian. How are you? Yeah,
Good. How are you?
very good. Thank you.
How are things going in Kleist?
Oh, not too bad, actually. I think we are still doing all the lectures online,
Yes.
but hopefully starting from next semester, we can go back to on-campus
Okay.
lecture. Yeah. How about you? How about the situation in Australia?
Yeah, it's much the same. We're just about to, tomorrow is the final day of second semester this year, so everything has been online. I think that we're preparing for next semester. I think it's still going to be a mixture of online and depending on the size of the class, but I guess there's going to be a lot more face-to-face next year. But that won't be until about late February, early March. So yeah. So do you know everyone here? So you obviously corresponded with John, who is coordinating this. Ari, who's our deputy head engagement.
Yes, I have been talking to Prof. Yeah.
And then
Hi.
Ken Tai Yong, who's our deputy dean.
Hi.
Hello.
And then Jingping, who's been, she works in our office as well. So yeah, so I think you're ready to go at 5 then?
Yes, so can I share, could you allow, okay, I can share my screen here, okay.
Yeah, I think John said you've got all privileges, so all of us have. The only thing that we'll do at the start is Jingping will put up a set of slides. We have what's called a welcome to country, and then I'll introduce you, and then you'll have the opportunity to give your talk, and then Ken Tai will coordinate the Q&A at the end, if you like.
Yep, I will.
So I just want to double check before we start. Can you see my screen?
Yeah, that looks
Yes.
good. Right? Yeah,
Yeah.
Okay, good.
excellent.
I'm ready to go.
Fantastic. All right. Was it almost 2 years since we saw each other, wasn't it? Was it in Daejeon? Is it? It's probably more.
I think when last time when you come to Christ, that was the last time I think.
End of 2018 for your school review, maybe?
Yeah, I think that's right. Yes, I think
Almost 3 years now. Jeez. Yeah, looking forward to meeting up again soon, either in Sydney
Yeah.
or Korea.
Actually, no. They have the ACAM, Asian Conference for Applied Mechanics. Do you know that there's the conference at the end of November?
This year?
Yeah, this year. Yeah.
Oh, okay. Yes. Yeah. And that's
Yeah.
in Seoul.
I think that's going to be online. It's supposed to be an in-person conference,
Yes.
but they changed it to online conference.
Okay. Yeah.
So I was supposed to go to Australia, but because it switched to online conference, so.
Oh, I think that might be yes. Was that meant to be run at Western Sydney? ACAM?
Oh yes, ACAM, yes.
Ah, of course. Okay. Yes. Yeah. No, it's still going to be online, I believe. Yeah.
And also I'm giving a plenary presentation at that conference, actually. Yeah.
Okay. So which university is coordinating that?
Alex.
Okay.
University of Adelaide. Yeah.
Oh, University of Adelaide. Yes. Now I do know. Yes. Alice Kutsov. Yes. Ah, very good. Yes, I do know. He ran a conference a few years ago, which I attended there. Yeah. Oh, that should be good.
Okay, so I don't want to hold you up anymore. So
no. Okay.
whenever
Anyway,
you're ready.
Good luck. break a leg, as I say.
Yeah.
Okay.
Looking forward to your talk and look forward to catching up soon.
Okay.
Okay, so, all right, John. So we're in your hands. Let us know.
Well, if we want to start with the running order was it's
Okay.
Jinping.
Jinping.
got
could
one
you-
now, so
Okay. Jinping, could you just share your slides and then we'll get Ari
Yeah,
to.
could you please stop sharing? So,
Oh, okay.
yeah, thank you.
Here you go.
Willie's made it. Hello, Willie.
Oh, hi, Willie. I'll just introduce you to, that's our Dean, Professor Sohn, Professor Svanapol, Willie Svanapol. Okay, so we're just going to start off with the welcome to country, I guess. So Ari, I'll leave it to you and then I'll introduce.
Okay. Okay. Good evening, everyone. I'm honored to invite you to the first lecture from the School of Civil Engineering in the series of distinguished lectures and initiative from the Dean of the Faculty of Engineering. Each lecture features a renowned speaker from around the world presenting about their work. These lectures are an opportunity for speakers to share their latest research with the academics and industry. Acknowledgement of country. Before we begin the proceedings, I would like to acknowledge and pay respect to the Gadigal people of the Eora Nation, whose ancestral land at the University of Sydney is built. As we share our knowledge, teaching, learning, and research practices within this university, may we all pay respect to the knowledge embodied forever within the Aboriginal custodianship of country. Now, I would like to invite Head of School, Professor Brian Yui, to introduce Professor Sohn. Professor Yui.
Well, thanks very much, Ari. It's a real great pleasure to introduce our first distinguished lecturer for the School of Civil Engineering, and it's a great initiative that our Dean has started. So we're really looking forward to Professor Sohn. So Professor Sohn is well known to us because we have an MOU between the University of Sydney and KAIST, and we've had a number of joint visits between our schools over the last number of years. Professor Sohn is currently Professor at KAIST in Daejeon in Korea, and he's a director of the 3D printing non-destructive center sponsored by the Ministry of the Science and ICT in Korea. He's published extensively in the areas of ultrasonic structural health monitoring, and more recently his group is doing work on the area of 3D printing. He's published extensively over 190 refereed journal papers and also a number of both domestic and international patents that his group have been involved with. He's currently a SPIE Fellow, member of the National Academy of Engineering of Korea, and a member of Korean Academy of Science and Technology. And tonight, or this evening, he's giving a talk titled Structural Displacement Estimation based on multi-modal sensing data fusion. So it's my great pleasure to invite Professor Sohn to give his talk. Thank you, Professor Sohn.
Okay, thank you very much for a nice introduction, Brian. And also I'd like to thank the University of Sydney for inviting me for this lecture series. Okay, so can you see my screen now? Okay. So I think I'm sharing the screen. Hold on. Okay.
Yeah, I can
So
see it
now,
now.
can you see my screen? Okay, good.
Yeah.
Okay.
All good.
So let me get started. So here is the outline of my presentation. So let me see. Okay. So first, I will talk about structural displacement estimation technique. Hold on, let me see. by combining RTK GNSS. This is too long to pronounce for me, so I'm just going to call it GPS. Okay, so we're going to estimate displacement by fusing GPS and acceleration measurements, and then I'm going to show you other example where we are combining our vision camera and acceleration for displacement estimation. And then I'm going to show you some laboratory and field test results. And then if I have time, I'm going to show you some other data fusion techniques. And then I will conclude my presentation. Okay. So first, so why it is important to measure structural displacement? And I think structural displacement is very important to understand global behavior of structures. And also displacement can be used for monitoring and also control, and then disaster prevention and mitigation. Okay. Then how about what is the common approaches for measuring displacement? Maybe one of the most common approaches is LVDT. So as you can see here, this is a contact type of the sensor. So you have to have this kind of a scaffold, okay? So that the transducer has to be in contact with the target measurement point. So we can apply this kind of technique for large scale structures. Another common approach is to use an accelerometer. So in this case, we can estimate displacement by double integration of the acceleration. But the problem is that it doesn't have good accuracy in low frequency range. Or people can use strain gauge, but strain gauge is quite noisy, and then it requires some prior knowledge of the Morse shapes to convert strain into displacement. And another common approach is this RTK GNSS. So we get signals from satellites. But the problem of GPS is that it doesn't have very good accuracy. The typical accuracy in the vertical direction is in the range of maybe 7 to 10 millimeters. Okay, and then these days, people are working on these non-contact sensing techniques. One of them is vision camera. Okay, so the problem is that this one is sensitive to lighting condition or weather conditions. And another approach is this laser Doppler vibrometer. Okay. And this one has very good accuracy, and it can measure vibration up to very high frequencies. But the problem is this one is very expensive actually. Okay, so sometimes also people try to use radar or LiDAR. And these days, other approaches is that people try to combine sensing data from different sensors. Okay, so for example, people try to combine acceleration measurements with GPS or strain gauge or vision camera. Or sometimes people try to combine LVD and LiDAR measurements together. Okay, and the first presentation I'm going to show you is kind of belong to this category. So we are combining acceleration and GPS measurements for structural displacement estimation. So this is our commercial sensor that we developed. So here, inside of the sensor, we have an accelerometer, and then we also have GPS chipsets. So they combine those two data, and then we can estimate displacement, velocity, and acceleration all together in 6 degrees of freedoms. Okay, and then this data is used for monitoring of several bridges in South Korea right now. And then here, I want to point out that to use this RTK technology, we need to have a base station at a fixed location. So compared to a conventional GPS, this RTK technology has better accuracy. But to do that, we need to have this base station placed in a fixed location. Okay. So this is overview of our commercial sensor unit. So inside it has a GPS chipset. So right now it can measure L1 and actually also L2 signals as well. And we are also working with a local company in South Korea to make this force balanced accelerometer. And then also we have a built-in data acquisition system so that we can get data from these sensors simultaneously, and then all the processing can be done inside the sensor unit. Okay. And then this is the picture of our actual sensor. So in terms of data fusion, we are using a two-stage Kalman filter to combine acceleration with high sampling rate and high precision, and GPS signal with low sampling rate and low accuracy. Okay, so initially we estimate displacement without considering the bias term in the acceleration. In second step, we estimate the bias produced by the accelerometer, and by combining them together, we can get a displacement with high sampling rate and also high precision. And again, in addition to displacement, we can get velocity as well as acceleration. That's the advantage. So here is some more details, but I'm not going to talk about the details, okay? And here is some nutshell explanation. So this is our measured acceleration. So we can estimate displacement by double integrations. So when we do double integration, we are introducing these integration constants. And by using a GPS signal, we are estimating these coefficients. So that's how we estimate the displacement. But in reality, it's more complicated than this. But this is kind of the nutshell explanation. And then we tested our sensor for several bridges in South Korea. And also we tested some bridges in China, Malaysia, and also in the United States. Okay. And now, as I mentioned to you, this sensor is commercialized, and it is deployed for several structures in South Korea. So here are two representative structures. The first one is Yeongjong Bridge, and second one is Incheon Bridge. So if you come to Korea next time, okay, so you're going to come to this Incheon Airport. And if you want to go to Seoul, you have to cross this Yeongjong Bridge. And then if you want to go to Daejeon, where the KAIST is located, then you have to cross this bridge. So for both of these bridges, our sensors are installed. So next time when you come to Korea, think about our sensors, please, okay? And also our sensor is used for monitoring this high-rise building and also landslide monitoring. So let me show you some data that we obtained from the Bay Bridge in San Francisco. We have done this testing in collaboration with Caltrain in California. So what we have done was we put our sensor at this location, okay? And we put this very expensive LDV at this at the bottom of the pier, assuming that there's no movement at the pier. And then we send out laser beam and try to get reflection to measure displacement. But because the angle is too large, we could not get very good reflection. So we put some reflector like this. So when we send out laser beam, it has some mirror on this surface, so we can get reflection right back. Okay, and then also we put our base station on top of this pier, assuming that the movement is negligible. Again, remember, the base station has to be placed at a fixed location. Okay, so that was the assumption. And here are the signals that we obtained. So this blue dotted line shows the ground truth value that we obtained by LVD. And then the red one shows the displacement estimated by our technique. And the error was less than maybe 2 millimeters. And this is our previous approach. And this is data fusion technique proposed by Professor Smith at Columbia University a few years back. And this is signal only from a GPS signal. So here we can see that there are quite a few drift at these locations. And not only that, here we see some spikes, okay? So overall, when we tested different bridges, Yeongjong Bridge, San Francisco Bay Bridge, etc., overall, the displacement estimation errors were less than 2 or 3 millimeters. Okay, so I think that the overall estimation error for vertical displacement was quite good. So now let me introduce some problems with GPS and discuss how we can address them. So first, in metropolitan cities like here, satellite signals are going to create multiple paths. So it doesn't go straight to the sensor. There are going to be a lot of reflections. So that's going to deteriorate the displacement estimation formulas. Okay? And also second, during and after some extreme events like the earthquakes, the base station is going to move as well. And then we cannot rely on the RTK technology for displacement estimation. And also sometimes satellite signals are going to be interrupted due to bad weathers or power outage. In that kind of case, it's going to create this kind of drift. Okay? So these problems can be addressed by fusing acceleration data with some other sensor data, such as a vision camera. Then how about underwater applications? So in this case, we don't have access to satellite signals. So I'm going to show you later on that we can use accelerometer and then strain gauges for displacement estimation. Okay, so this presentation mainly focusing on displacement estimation under GPS denied environments. Okay. So here is the overview of our data fusion techniques. So we basically combine high sampling rate and high accuracy acceleration with some initial displacement estimated from different sensors. And we combine this data using either Kalman filter or FIR filter, so that we can estimate displacement with high sampling rate and high accuracy. Okay, so first I'm going to show you some examples by combining vision camera and then acceleration measurements. So first, so this is kind of overview of the proposed technique. So first, when we take images, we can trace the movement of some features in subsequent images. Okay, and then we can compute translation in the pixel unit. And then once we have some scaling factor, we can convert translation in the pixel unit into displacement in the physical length unit. Okay. And later on, I'm going to show you how we can estimate this scaling factor. So to demonstrate the basic concept, let me show you some experiment. So this is our target here. Okay. And then we put on accelerometer and then vision camera on top of shaking table. So this shaking table is moving up and down. And then we have this LVD for reference displacement measurement. So now the shaker is moving up and down like this. Okay. So first, let me show you how conventionally scaling factor is estimated. A lot of time we assume that the physical size of the target is known. Okay, so if I know the physical size of the target and then the corresponding number of pixels, then we can compute the scaling factor very easily. Okay, but in reality, many cases, the target is going to be located far away from the sensor, and it's going to be difficult to know the physical size of the target. Okay, so in our proposed technique, what we do is we initially estimate displacement from acceleration through double integration, and also from vision camera, we estimate translation in the pixel unit. And when we compare them, we look at the responses only for some specific frequency band. The reason is like this, because if you look at the acceleration response in low frequency range, they are not reliable. And also, if you look at the vision image in very high frequency range, they are not reliable either. So we are kind of choosing some frequency band to compare the displacement from acceleration and translation from vision camera. So we can look at their relationship, and then most likely they're going to have this linear relationship. And this slope represents the scaling factor. So in this way, we can automatically estimate the scaling factor without knowing the physical size of the target. Okay. So once we know the scaling factor, now I can trace the relative movement of these targets, and then we can get initial displacement from vision camera, and then combine this initial displacement with acceleration measurement so that we can improve the accuracy of the displacement. Okay. So now, next, let me show you how we can trace the movement of this target. So in the conventional approach, we define this region of interest in the first frame, okay? And then the target inside this ROI is continuously traced in subsequent images. Okay, but as you can see here, when we have large displacement, sometimes the target can be outside of this ROI. And this can be a problem. Okay, so what we do is, we initially define ROI, and using Kalman filter, we can kind of predict the movement. And based on the prediction, we can move our ROI. Okay, so in this way, we can make sure that the target structure or target going to be inside of the ROI all the time, even when we have a large movement. Okay, so for a translation estimation between the first frame and then the current frame, we first extract features from the target. Okay, and then we compute a translation for each target or each feature. And by the way, in this example, we are estimating only the vertical translation. Okay, then we can get a vertical translation from one feature and repeat this procedure for several features. Okay, and then we can get the distribution of this translation. And also using Kalman filter, we can predict this interval. Okay, so this is corresponding to maybe kind of 6 sigma. Okay, and then sometime we might have some translation which is outside of this interval. So this is corresponding to some mismatch. So mismatch means that this feature is supposed to match to this point. But sometimes we can have some mismatch, right? So we can automatically reject these mismatch points, and then we can compute the average translation value. And this average translation becomes the movement, the translation of the target. And then we adjust the ROI according to this average translation value. Okay, so here's an example. So using our proposed approach, we can see that we can have pretty good matches of these features. So here the number of matches were 19, but without proposed technique, we can see that sometimes the target can be outside of the ROI. So we have less number of feature matchings. So we have less accuracy. Okay. So once we do our feature matching, and then we can compute the average translation for the target. And then I showed you how we can compute the scaling factor. And then we can easily compute the displacement at some point. And then we repeat this procedure between the first frame and then the next frame. And then we can compute displacement at the next frame. Okay. So now here, let me show you how we combine multi-rate data. So here we assume that displacement and acceleration have different sampling rates, but we assume that they are synchronized when they are collected simultaneously. Okay, and then here is the state space model. The state vector has displacement and velocity. Okay, so for the state vector estimation, there are two cases. In case one, when we have only acceleration measurements, in that case, our state vector is estimated only using acceleration. So this is a prior estimation, and posterior estimation is equal to a prior estimation. And second, when we have acceleration and then displacement from vision camera simultaneously, and then as you can see here, our state vector is estimated using the displacement at current time point, and then this one is obtained from acceleration. Okay, but in reality, many cases, there will be some offset between those two measurements. So that are going to be synchronous. So in our approach, we assume that acceleration and displacement have different sampling rates, but also they are not synchronized. Okay? Under this assumption, we have three different cases for state vector estimation. So first, when we have only acceleration, so this is equal to the previous case. Okay. In case 2, when we have only displacement, so like here. So in this case, we don't estimate displacement. Here, we only estimate the gain matrix. And in case 3, when we have acceleration, and then displacement can be anywhere between this interval, like here. In that case, again, displacement is estimated using the displacement right here, and then using acceleration and then displacement. And also we use this Kalman gain that we estimated previously. Okay, so here I want to point out that our technique can handle asynchronous multi-rate data. So let me show you some data. So this is the test setup that I showed you previously. Again, we have our accelerometer and the vision camera on top of the shaking table. And this one is moving up and down. So we put 3 different types of excitations to the shaking table. So here we put a sinusoidal excitation, and here we put a sweeping signal. And then here we actually recorded real bridge vibration, and we put that one as input to the shaking table. And so this is the displacement estimated by estimated only using a vision camera. Okay, and this is the displacement obtained by our proposed approach. So here we can see that we can improve the accuracy about 20%. Okay, so here. So overall, the error was less than 1 millimeter. Okay. So next, we repeated a similar test, but here the distance between the sensor and natural target was about 52 meters. Okay, so this is our natural target. Okay, and then we put sensor on top of this 4-story structure, and this 4-story structure was placed on top of our office building. Okay, and then the shaker was producing again the vertical movement. So to use a conventional approach, the people have to go to the window, and then they have to measure this physical size of the window, so that we can estimate this scaling factor. But in our case, again, we don't need to know the physical size of the window. All we have to do is we combine data from acceleration and vision camera, and then we can automatically estimate the scaling factor. Okay, so this is our actual setup. And also we use this laser sensor to get the reference displacement. So again, we put sine wave and then sweeping signal. And also we are kind of producing a pseudo-static displacement. In all cases, the error was less than maybe 4 millimeters. Oh, I'm sorry, less than 3 millimeters. And again, compared to a vision system, we were able to improve the accuracy. Okay, and here, compared to the previous example, the error level increased slightly due to the increased distance to the natural target. So in the next example, we have done some pedestrian bridge test. So here is our sensor unit, and we try to measure the vertical vibration. And this is for reference vibration measurement. And we use this traffic light support structure as target. And the distance was only like 2 meters. And then the bridge was excited by a jumping and then walking of students. Okay. So here is the result when 4 people were jumping. And here 1 people were jumping and 16 people were passing through the bridge. And here 16 people were slowly passing through the bridge. So in all cases, the error was less than actually 1 millimeter. And this is result using a vision camera. And we can see that we were able to improve the accuracy quite a bit. And also, we can use this vision and acceleration fusion system for estimating permanent displacement after an earthquake. And again, remember that we cannot use the RTK technology since the base station is going to move during the earthquake, right? So what we do is first we take vision images before and then after the earthquakes. Okay, and then we perform feature matchings, okay, like this. And then find feature groups where the variation of displacement is very small, like these locations. And this location indicate locations where the structure did not move that much. So what I mean by that is, due to earthquake, you can see that some of these features are moving quite a bit, but the base did not move that much, right? And then we compute the mean value of these feature groups or displacement. So we compute the mean value to estimate the permanent displacement. Okay, so here let me summarize the uniqueness of the proposed acceleration and vision-based displacement estimation technique. So first, we were able to estimate a scale factor automatically by combining acceleration and vision measurements. And also, we were able to update ROI automatically so that we can also trace large displacement. And also, we proposed some automated mismatch rejection algorithm so that we can improve our feature matching procedure. And also, our technique can be used for fusing or synchronous multi-rate data. So now, next, let me show you some other data fusion example. Okay, so here we're going to combine acceleration and then radar measurements. So one of the problems with the vision camera is that it cannot be used during the nighttime or under foggy or raining conditions. So one alternative is to combine acceleration and radar measurements. And also, while the vision camera is effective for measuring in-plane displacement, radar is more attractive for measuring out-of-plane displacement. Okay, so let me first explain the basic working principle. So first, we send out incident waves to some target point, and then we measure reflections. And then by comparing those two signals, we can compute the phase. But here, the problem is that there can be multiple solutions because the ambiguity of these sinusoidal signals, right? So they are apart by 2 pi. So what we can do is, using acceleration, we can predict the phase shift, even though it may not be exact. And then we choose the phase which is closest to the prediction obtained by the accelerometer. And then using a scaling factor, we can convert this phase shift to displacement. Actually, initially we convert a phase to displacement along this line of sight direction, and then subsequently we can convert it to the displacement in the actual vibration direction. And then next, we repeat this procedure again and then estimate displacement at the next time point. But as you can see here, actually this time interval is going to be large. So the sampling rate is going to be limited, okay? And then once we estimate this displacement, initial displacement, then we can combine with acceleration, just like the previous approaches. So we have done similar testing, just like before. So here, so in this case, again, we put this 4-story structure on top of our building. So we have our accelerometer and then millimeter wave radar. And this time the structure is moving in horizontal direction. Okay. So this is our configuration. So now, like before, we put sinusoidal excitation. So the red one is the proposed approach. And this is the conventional, the blue one is the conventional radar technology. So here what we can see is, we can see that there's some drift right here, right? So what happened was, because there's some ambiguity, instead of finding the correct phase shift, sometimes they are picking some wrong phase shift information. That's what happened. Then we can see some drift, even for this sweeping signal. So for this bridge vibration, it was okay. But as you can see here, as we get more and more data, we can see that the error is accumulated. Okay. And using the proposed technique, the estimation error was less than 1 millimeter. So this was pretty good. And then we have done similar testing for pedestrian bridge, just like before. So this time we are putting waves in the vertical direction. And also we have people walking down the bridge. So this is the displacement from the proposed technique, and this is the existing technique, meaning that only using the radar measurement, and this is the ground truth value. So in all cases, the error was very, very small, actually less than 1 millimeter. So next, then how about underwater applications? So in this case, we cannot use none of GPS, vision, or even radar. And our department at KAIST has a large-scale project funded by our National Research Foundation of Korea for developing key enabling technologies for design, construction, and maintenance of these submerged or floating tunnels. And as part of this project, I'm developing a displacement estimation technique for underwater applications. So in this case, what we do is we combine strain gauge measurements with acceleration. So here the key is how to estimate initial displacement from strain gauge. Okay, so once we get the initial estimation of displacement, and then the rest is pretty much same as the previous approaches. So the basic concept is that if I know the mode shape for the displacement, so this is the mode shape, and this is the second derivative of the mode shape, and then if I can measure strain at 2 locations across the cross section of the tunnel, then we can estimate displacement. Okay, of course, in many cases, we will not know the exact mode shapes, right? So I'm not going to explain the details, but we also have some procedure so that we can introduce some compensation factor to consider the discrepancy between the actual mode shapes and then the assumed mode shapes. Okay, so then to test our idea, we have done several testing. Hold on. So, we have done like the actual testing. So like this, we made several specimens. Yeah. And we actually put them on the water, okay? And then, yeah. And then we actually put some, create some waves, and then we can see the vibration of the tunnel like this. So we do testing until the failure of these tendons, okay? So here is another test specimen. So this is our tube here. And then we put strain gauges at 6 different locations. And at each cross section, we put 3 strain gauges. We need those 2 to measure our vertical deflection. And we need those 2 to measure our horizontal deflection. And also we put accelerometers at these 5 locations. And then you can see that, can you see that there's some metal sticking out at these locations? And we put some markers, and then we put camera somewhere here so that we can get a reference displacement. Okay, because again, under the water, we cannot measure displacement precisely. right? So again, we produce waves, and then using this camera, we can get the reference displacement. Okay. And then this is the horizontal displacement obtained by strain gauge. And this is the one obtained by our proposed approach. So we can see that we can reduce the error significantly. And then this is the vertical deflection from strain gauge and using our proposed technique. Again, we were able to reduce error maybe like around 40%. Okay. And we can see that there are some waves coming in and coming out and coming in again. Okay. So this is the last page. So if you have been sleeping during my presentation, it's time to wake up. Okay. So in this presentation, we are presented 4 multimodal data fusion techniques to estimate structural displacement, especially focusing on GPS denied environments. So what we do is we always try to use acceleration measurements and then try to combine acceleration measurements with either GPS or vision camera or strain gauge or radar. And for the vision and acceleration fusion technique, the uniqueness is automated scaling factor estimation, and also automated ROI updating. And also we improved our feature matching algorithm. And then our technique can be used for asynchronous multi-rate data fusion. And then the effectiveness of the proposed technique was validated through laboratory and field tests. And in many cases, the error was less than 2 or 3 millimeters. Okay. Well, I have to mention that we have done only a preliminary test, so there are many limitations. First, we have done testing only for a short distance, maybe only up to 50 meters. And then displacement was estimated mainly in 1 or 2 directions. And eventually, we want to estimate displacement in 3 directions. And also, all the testing was done only for a short time period. So the long-term performance has to be validated in the future. And also, personally, the advantage of using these data fusion techniques instead of using GPS is that these sensors consume much less power than GPS. So it's going to be more attractive for wireless sensor developments. So that's what we try to do in the future. So with all that, I'd like to thank you for your attention. And also, I'd like to thank all of my students for their hard work. And I have one small announcement. I'm always looking for motivated students. So if you are interested in working with me, please contact me at this email address. And thank you very much for your attention.
Thank you, Prof. Sohn, for your wonderful talk. We have learned a lot, from your lectures, and I think many of our colleagues, have benefited from it. And I would like to encourage, our USIP colleagues, to discuss possible collaborations, with Prof. Sohn, and this will surely further strengthen our relationship with KAIST. With that, let us move on to the Q&A sessions. Please raise your hand, if you have any questions, and we'll do this on a first come first serve basis. Or if you can type your questions, into the chat box, and I will direct the question to Prof. Sohn for answering your queries. So at this stage, let us move on to the Q&A sessions. Anyone?
Okay. I see one.
Oh, it's a thank you. It's not a question. So it says, oh yeah, thank you so much for your presentations. There's a questions, from Mawson's. So his question is that, have you ever considered window estimations?
Okay, so what kind of smoothing? Okay, so that's a very good question. So, for Kalman filter, we are not using any smoothing. The reason is that as soon as you introduce smoothing, that's going to produce some time delay. So we cannot do real-time estimation. So a lot of time we try to avoid smoothing for Kalman filter. But if you want to improve the accuracy, yes, you can introduce some smoothing, but at the price of some time delay. Okay? So I hope that this answered your question. Good.
Any other questions?
How about constraint optimization in calculation of Kalman filter? Okay. Yeah, actually, that can be another approach. And actually, constraint optimization works very well if I can assume that at the end, the displacement goes to 0. Okay, that's a lot of assumption when people use for constraint optimization. But as you can see in my presentation, sometimes we might have some permanent displacement, like the earthquake example, right? In that case, we cannot use that kind of constraint. So because I want to look at some earthquake applications, I try not to use that kind of constraint optimization. Okay. Okay, so here's another question. How do I calibrate the noise parameters? So I think for this one, you're referring to Kalman filter, I guess. So let's see whether I can show you the equation. So this is the problem when you have too many animations. Yeah. And I think she is referring to where is yeah. So some of these noise terms, right? So for acceleration, before we start the vibration of the structure, we can estimate the noise level relatively well. So for acceleration, it's okay. But for vision camera, we don't have very good estimation of the noise level. Okay, so most likely we have to rely on the acceleration measurement, and then we have to assume relatively large noise for the camera at the beginning. And as you can see here, as we continuously update Kalman filter, we are also updating the noise covariance metrics. And eventually the noise is going to converge. Okay, so that's how we address the noise issue. So there's another question. Okay, so any other questions?
Good.
Okay, thank you. Yeah.
Any other questions?
Thank you. So feel
Right.
free to contact me by email anytime, okay?
Sounds good then. So if not, I think I'm actually aware of the time. So if not, let us again, thank Prof. Sohn for addressing all these questions. We really appreciate his support on our lecture itself. Jinping, can you actually please share the slides?
Oh yes, or I can send, or maybe I can cut down some of them and send you those slides, okay?
Thank you. So thanks. So before we end our lectures, we'd like to express our appreciations, for Prof. Sohn's support on our distinguished lecture series. And the schools of civil engineering will be sending this gifts, to Prof. Sohn, and this gift will serve as a good remembrance, of our relationship. At the same time, this serving as a kind of a solid foundation, for us to move on with various kinds of collaboration in the near future, especially the right now the border is actually opening up and giving us more opportunity for Prof. Sohn to come and visit us, and we'll be also having the opportunity to visit Prof. Sohn, in Kais. I'll certainly remember the sensors when I actually crossed the bridge, Prof. Sohn, saying that, hey, I have a friend, who actually built the sensors for these two bridges. One is actually in Incheon, the other one is actually in the other bridge itself. So, again, so at this point, let us wish Prof. Sohn, his ever success, in his career in Korea. And with that, again, thank you everyone for participating in this distinguished lecture series. So, Brian, do you have anything to follow up before I end this session?
Oh, no, thank you again to express my deep congratulations to Professor Sohn, and also thank you for everyone for joining. Hopefully we'll have another distinguished lecture next year. Wish everyone all the best, and thank you for joining us today. Thank you, Kentai, for doing the Q&A. Yeah.
Thank you. Thank you, everyone, then. All right.
Thank you very much for having me. Bye-bye.
Bye-bye. Thank you.
Bye. Thanks, John. Thanks, Ari. Thanks, Professor Sohn.
Bye-bye.
We'll be in touch. Thanks, Ari. See you, Ari.
Thank you everyone for attending. I will be ending this webinar shortly.